Okay, so the session is being saved, recorded, and now I'm going to share my PowerPoint. Okay, can you see my screen now? Okay, perfect. So, in the previous class, we were talking about, let me see where we were. So, in previous class, we are talking about phase and line voltages. Now, I want to move towards solving a couple of examples and also working on different connections. Okay, so sorry, I'm trying to see how I can manage this. Okay, finally, I found where I wanted to start. Okay, sorry for the delay. So what I want to discuss here is how we can analyze a circuit if the circuit is Y delta connected or delta Y connected or even delta delta connected. So if you have anything other than Y, interesting. Now my pen is not working. Gosh. Okay, I think I have to close my PowerPoint because it doesn't let me draw on it. Just give me a couple minutes. Okay, I think now my pen is working. So hopefully I don't have any other technical difficulty anymore. So in order to have a circuit that is not Y-Y connected, we know how to deal with a Y-Y connection. But what if our circuit is not Y-Y connected? If we have a Y delta or delta Y connection, we have to convert it. So I'm going to draw what we have here. So let's say this is the delta here. So this is what we have, and here we have A, B, and C terminal. If you want to replace this with its equivalent Y connection, so we have the delta and we want to replace it with the Y connection, then please, so it's a little bit hard for me to go back and forth between the PowerPoint and the meeting. If you have any question, just use your microphone, or if you can't. Are you able to see the screen?
We can't see what you're drawing.
Oh, you can see the screen? Okay, thank you. Let me reshare it. Can you see the drawing right now?
Yes.
Okay, perfect. So let's assume that we have this delta connection and we have an impedance for each phase of this connection. If you want to convert it to its equivalent Y connection, so in a Y connection, basically we have something in this form. So you want to replace it with some impedance that is, if you use it with a Y connection, then it's going to behave exactly the same way that the delta connection will do for your circuit. So in terms of the current and the voltages of the line, it's going to keep all the voltages at A, B, C terminal, and the currents going through these three terminal, it's going to keep them exactly the same. We don't care about what's going on internally. So we are trying to find the equivalent circuit in Y connection where it's going to keep everything on ABCD terminal the same way that it's going to be with delta connection. Now, I'm not going to show you the proof, but it's a very simple equivalent circuit. All you need to do is dividing your Z delta by 3. So for example, if your Z delta is 3 plus J9, then its equivalent Y impedance, so ZY, would be 3 plus J9 divided by 3, which is 1 plus J3. And then this is something that you can use for each phase of your circuit in Y connection. And then when you have the YY connection, you can easily go back and convert it into a one phase equivalent circuit and you can solve everything. Now, so a bunch of things that are very important here. First of all, is every value that you plug into your single phase diagram should be a phase value. So it should be a phase voltage, it should be phase current, it should be phase impedance. And in terms of load impedance, it should be the impedance of the Y connection. You cannot use the delta connection. So this is how you're going to convert it into Y, and then you have the ability to draw your one phase circuit. Okay, so the next topic that I want to do, let's see. Can you confirm that you still have my screen?
I cannot see your
I
screen.
can't see your screen anymore.
Oh, it doesn't? Okay, thank you. Okay, so here I want to solve an example so you can see how we can use a single phase diagram. Let me draw the circuit here. So let's assume that we have a 120 volt source. Actually, let me draw the questions. I'm going to show you how the question will look like and how you're going to convert it into a single phase diagram. So let's assume that we have a generator. And the generator is a positive sequence. It has Y connection. And the problem is saying that we have 0.2 plus J 0.5 ohm per each phase of the generator. This is how we show each phase impedance. So ohm per phase is the unit for that. And then the voltage of each phase is 120. The voltage of the magnitude of each phase is 120 volt per phase. So this is the generator. And then let's assume that we have a load. And the load is also Y connected. So here we don't need to convert any of them to Y because both of them are already Y connected. And then the load is also 39 plus J 28 ohm per phase. So we know the impedance per phase for the load. And the line of this circuit, and the line is basically the cable or the impedance that is connecting the generator side to the load side. And the line is 0.8 plus J 1.5 ohm per phase again. So these are the information that we have, and having this information, I should be able to draw the single phase diagram. In order to draw the single phase diagram, I'm going to start with the generator. I have 120 volts per phase, so it's going to be 120 with an angle of 0. And then there is an impedance in each phase. So I have a resistive and a capacitive impedance, which is 0.2, and then J 0.5 per each phase of the source. The line is given as 0.8 plus J 0, not 0, 1.5. And then I also have the load. The load is also inductive. So it's going to be 39 plus J 28. So as you can see, it's very simple to draw the single phase diagram of the circuit. The only thing that you have to be careful in this problem, it's very simple, but the only thing that you have to be careful about is, first of all, here I'm using the impedance right away because I know that the connection is Y. If it's a delta connection, it needs to be converted. So you need the Y equivalent impedance for the load, or if that's the case for the generator. And then another thing you have to be careful is that the voltage that is given here is the phase voltage. If you have the line voltage, it needs to be converted. So these are the things that you have to be careful about. If the load is delta, you need to convert it to Y. If the voltages are given in form of line voltage, you need to convert them into phase voltage. Anything in single phase diagram that you are plugging here should be phase value. So if you have a current and it's line current, it needs to be converted into phase current. If you have voltage and it's a line voltage, it needs to be converted into phase parameter. So this is the important part. Other than that, drawing the single phase diagram is not going to be difficult. Okay, so this is the first part of the problem. And then the next part, it's asking for the current, the line current. So it's explaining the line current as IAA, IBB, and ICC. So I'm going to go back to the previous. So here, focusing on this single phase diagram, this is basically IAA. Now, do I need to solve separately for them? The answer is no, because the circuit is balanced. Since the circuit is balanced, I'm going to solve only for the current in phase A, and then I'm going to shift it in order to get the current in phase B. So I'm going to have IAA as the voltage that I have in the loop, and that was only the 120 with an angle of 0. And all the impedances I had in the loop was the impedance of the generator being 0.2 plus J 0.5. And then the other one was 0.8 plus J 1.5. And the impedance of the load was 39 plus J 28. So if I do the calculation here, I'm going to have IA capital A as 120 divided by 40 plus J30, and that's equal to 2.4 with an angle of minus 37. So this is the current of phase A. Now that I have the current of phase A, I know that the circuit is balanced, so I can easily say IB capital B has the same magnitude, and the phase angle is equal to minus 157. So all I'm doing is subtracting 120 degrees from the angle. And IC capital C is 2.4 with an angle of 83, and for this one I need to add 120 degrees. So in a balanced circuit, you have an easy job to do. All you need to do is solving for the phase current or voltage or whatever parameter you're interested in, and then you have to just shift it with 120 and minus 120 to find the other two phase parameter. Any question up to here? Okay, so the next part of this problem, what I want to do is part C. It's asking for the load phase voltage. In this chapter, you have to be very careful about how the words are being used in this for the problem. So here I'm using for the load voltage, and specifically, I'm looking for its phase voltage. The nice thing about this part is the phase voltage is what I'm going to get with single phase diagram. So when you have a single phase diagram, anything that you plug into, so let's say this is your single phase circuit, any parameter that you are plugging into the circuit should be phase parameter. And anything you calculate is also phase parameter. So if I'm looking for the phase voltage, I don't need to be worried about, because the single phase diagram is going to give me the single phase and the phase voltage. So I'm looking for the load voltage, and load voltage is here, the voltage across this load. In order to solve for the voltage of the load, I need the impedance of the load multiplied by the current of the load. So that's simply an Ohm's law. So VA capital N is equal to load impedance, which is 39 plus J28 multiplied by the current of this phase, which I just calculated. And that was equal to 2.4 with an angle of minus 37. Okay, so if I do the calculation here, I'm going to get VAN, or the phase voltage of the load at phase A, as 115.22 with an angle of minus 1 degree, right? So I have this. And then in order to solve for VBN and VCN, all I need to do is adjusting the angle. So the magnitude is going to stay exactly the same. The angle here is going to be minus 121 degree, and here it's going to be positive 119 degree. So here I'm subtracting 120 and then adding 120. So it's very simple because the circuit is balanced. The next part of this problem, it's now asking for the line voltage at load. So it means that I'm looking for the voltage of the load, but not the phase voltage. It's the line voltage at the load terminal. So if you need the line voltage, all you need to do is solving for VAN, which is the phase voltage, at load. And we calculated this one as 115.22 with an angle of minus 1 degree. So what I have to do now is simply adding radical 3 to the magnitude. So I'm looking for VAB, VBC, and VCA. All I need to do is adding a radical 3 to the magnitude, which was 115.22. And then the angles is going to be, the angle would be 29 here. So I'm going to add 30 degree first to the first one. And then I'm going to subtract 90 degree here. And then I'm going to add 150 degree here. So this one is going to be minus 91 degree. And this one is going to be 149 degree. So as you can see, if you have the phase voltage of a particular element in your circuit, which is the load in this case, then you can easily convert it into line voltages. There's no calculation. All you need to do is multiply, basically amplifying the magnitude by radical 3, and then adjusting, shifting all the angles by 30 degree. If you want to think about them, if you know this one, in another word, you can just subtract 120 here and then add 120 here. So again, it's shifting all the vectors by 30 degrees. Okay, let's see what is our next question. Here it's asking for the line voltage at the source. So I'm going to show on the circuit what exactly we are looking for. So this time it's looking for line voltage at the source. So here is the source. So it's asking for the voltage here. And it's asking for the line voltage at the source, which means I'm not going to be able to directly solve for the line voltage of the source. I have to solve for the voltage, phase voltage first, and then I can convert it into the line voltage. So when you have line voltage, what you have to do is first, you have to calculate the phase voltage. And then when you know what is the phase voltage at source, you can easily convert it into line voltage. So this is what I have in my circuit. This is the circuit, and I'm looking for this voltage. In order to solve for this one, you can say it's 120 with an angle of 0. So VA capital N is 120 with an angle of 0 subtracted by the voltage drop that I have here. And this voltage drop is equal to IA capital A multiplied by the impedance of the source. So it's going to be 120 subtracted by 2.4 with an angle of minus 37. This is the current line. And then the impedance. And the impedance of the source is 0.2 plus J 0.5. So if you do the calculation, it's going to be 118 degree, 0.9 with an angle of minus 0.3 degrees. Now I have the phase voltage now. If you have the phase voltage, all you need to do in order to find the line voltage is multiplying this value by radical 3 and then subtracting this, multiplying by radical 3 and adjusting the angle. So radical 3 by 118.9 with an angle of minus 0.3 plus 30 and then minus 90 and then plus 150. Okay, any question up to here in the example? If you don't have any question, I'm going to move to the next part of this chapter, which is about power calculation for a three-phase system. So if you have a three-phase circuit, then you also want to know how much power this three-phase circuit is consuming or generating. In order to do that, we have to follow two steps. The first step is going to be calculation of one phase power, and then having the power consumed in one phase, we can easily find the power consumption in other phases as well. So in the first step, let's assume that the circuit is balanced, and having a balanced circuit, I know that, for example, the voltages are all the same. So I know the magnitude of VAN is equal to the magnitude of VBN, and it's equal to the magnitude of VCN. And then regarding the current, I also know the current magnitude is also the same. If it's balanced, all the currents magnitude are going to be exactly similar. So this is what I have. Let's call the voltage magnitude as V phi just to be consistent, and the current magnitude as I phi. So if the load is balanced, in a balanced scenario, if I want to calculate the current, if I want to calculate the average power, then I have the power of one phase, for example, phase A, being equal to the voltage of this phase multiplied by the current of this phase multiplied by the cosine of theta v minus theta I, right? So if I'm calling this one as V phase and this one as I phase, so I can simplify this into V phi I phi cosine of theta v minus theta I. Now, if this is for phase B, then it's going to be the same voltage, the same current, cosine of the difference between the angle of the voltage and current. Can you tell me if I have a different angle or not? So I want to know. I know that the magnitudes are the same, and that's why I'm using the exact same magnitude of V phi and I phi for every single phase of the circuit. But can I use the same theta v minus theta I for phase A, phase B, or phase C? Does anyone have an opinion on this? Okay. You probably are guessing about if this can be the same or not. So if I have, for example, let's say this is the current and this is the voltage in phase A. So this is IA and this is VAN. This is what I have as theta V minus theta I. If I'm focusing on another phase, IA is going to be 120 out of phase with this one. VBN is also 120 out of phase. So what I have in another phase is this one. This one is 120 out of phase. So probably I have, for example, in phase C, I have this for the current. This can be ICC. And then this can be VCN. So both of them are shifted by 120 degree, but what is going to be exactly the same is the difference. Because I'm shifting both of them by 120 degree, then the difference is going to stay the same. So theta V and theta I individually are not going to stay the same, but the difference is going to be the same. So I can just assume that it's still theta V minus theta I. So what I have here is basically for phase B is theta V minus 120 being the angle of voltage, and then subtracted by theta I minus 120. These two will cancel out each other, and I get the same angle again. So now what you can see is that the power of phase A is going to be exactly the same as the power consumption in phase B, and it's going to be the same for phase C as well. So according to this equation, and knowing that this is going to stay the same, and these are the same actually, then we know that the average power of phase A is going to be exactly equal to the average power of phase B, and same as average power in phase C. Let's call all of them as the phase power consumption. So this is the important conclusion up to here, that P of each phase is equal to the magnitude of the voltage multiplied by the magnitude of the current multiplied by the cosine of theta V minus theta I. Now, if I have all three of, this is going to be the same for all three phase. If I need the average power consumed by the whole load, then what I have to do is multiplying the power by 3 to get the total average power of the load. So the only difference that shows up here is that if you are working with one phase, you're going to do this calculation. You're going to say, okay, the average power for this single phase diagram is equal to V phase multiplied by I phase multiplied by cosine of theta V minus theta I. But if you are looking at a three-phase scenario, then the power of this three-phase circuit is equal to 3 multiplied by each phase power. And that would be equal to 3 multiplied by V phi I phi cosine of theta V minus theta I. So this is the whole three-phase power consumption. Now, the interesting part is that you can also convert this equation into an equation where you have the voltage and current of the line instead of the voltage and current of the phase. So according to this equation, if you want to use this equation for power calculation, you have to plug the voltage, the phase voltage and the phase current. But sometimes instead of phase voltage and phase current, you have the line voltage or the line current. So we want to see how we can convert it into line parameter. So let's see what is the relationship between the phase and line parameter. If we have a Y connected load, sorry, my pad is. So if you have a Y connected load, we know that in a Y connection, the current of the line is exactly equal to the current of the phase. Regarding the voltage, we know that the magnitude of VL is equal to radical 3 by the magnitude of V phi. So if you want to replace them, instead of I phi, you can directly replace it with IL because in a Y load, it's going to be the same. But for V phi, you can replace it with VL divided by radical 3. So according to this equation, if you want to replace V phi, you can replace it by VL over radical 3. Again, the angles are going to stay the same because even if you are focusing on line current and line voltage, you are shifting all of them by 30 degrees. So it doesn't make any issue. Now, what we have here is this 3 over radical 3 is equal to radical 3. So our equation, our three-phase power average power equation is going to be radical 3 VL IL cosine of theta V minus theta I. So a conclusion here is that, let me erase some of these extra things. So my conclusion at this point is, if you have the V phi and I phi, then you need to use 3 because you're focusing on each phase. You have to multiply it by 3 in order to get the total. But if you have the line parameter available, then you don't need to convert them into phase parameter. You can directly use the line parameter, but just be careful that the power is going to be radical 3 multiplied by VLIL if you're using the line voltage and line current. So what we did here is we use it for Y load, but to be honest, even for delta load, it's going to be the same. Why it's going to be the same? Because it's going to be just a different scenario. So here in VL is exactly equal to V phi, so you can directly replace it with VL. And then IL is radical 3I phi. So again, this radical 3 is going to pop up in your equation because this time, in order to plug IL into your equation, what you need is IL divided by radical 3. So 3 over radical 3 is going to be the same. So even though I have used either Y or delta load in order to replace the line parameter, it doesn't really matter what is the load type. Eventually, it's going to be a radical 3. So if you are using the line parameter, you need to have radical 3 as the coefficient. If you are using the phase parameter, you need to have a 3 as the coefficient. So either way, you can calculate your average power. Okay. So the next part is how we can calculate the complex power. For the complex power, we need to have the reactive power as well. And reactive power is going to be basically the same thing, with the exception that instead of cosine, we are looking at sine. So the P of one phase is equal to V phi, I phi, cosine of phi. Let's call theta v minus theta I as phi. And then Q of each phase is equal to V phi I phi sine of that angle. So if I'm looking for P total, I can go with 3 one-phase power, and that is equal to radical 3 VLIL cosine of phi. And for Q, it's going to be 3 multiplied by one-phase reactive power, which is radical 3 VLIL sine of this angle. Now, if I need to have the complex power, then it's going to be P total plus JQ total. And that would be radical 3 VLIL multiplied by cosine of theta, cosine of phi, plus J sine of phi. And this is basically an angle, one with an angle of phi. So if I need the complex power, S would be equal to radical 3 VLIL with an angle of phi, or I can also explain it as 3 V phi I phi with an angle of phi. Either way, I have a correct answer. Now, does it matter if I have a delta load? If you have a delta load, you can transfer it to a Y-connected load. You can calculate ST, PT, and QT, the total. But the final conclusion is that it will be the same. So when we are calculating, we are doing any power calculation, it doesn't matter if the load is either Y or delta connected. So it doesn't matter if you have a Y or delta connected, as long as you're using either phase or line parameter, you're plugging them into the equation, you're going to get the exact same, exact correct value at the end. The next part that I want to discuss is instantaneous power. So Here, what you can see is the voltage at each phase and the current at each phase. And this is actually the angle difference between them. It's called theta phi here. If I want to focus on the instantaneous power of a three-phase circuit, what I have is I want to solve for PT, which is the multiplication of VT by IT. So in phase A, it's going to be VMIM cosine of omega t multiplied by cosine of omega t minus theta phi. In phase B, it's going to be Vm because it has the same magnitude, Vm cosine of, the angle here is going to be subtracted by 120 degree, and then same thing for the other angle, cosine of omega t minus theta phi minus 120 degree. And then for phase C, it's going to be Vm cosine of omega t plus 120 degree cosine of omega t minus theta phi plus 120 degree. Now, what will happen is that if you add all these three together in order to get the three-phase instantaneous power, you're going to have P of t equal to 1.5 Vm Im cosine of theta phi over cosine of theta phi. So this is the instantaneous power. So the interesting part is that even though in each phase you have an instantaneous power which is changing over time, but if you look at the instantaneous power of all three phases at the same time, the summation is always fixed. So you have a fixed number, fixed amount of power at each moment being transferred. So it doesn't matter if it's now or if it's 10 seconds afterward or whatever is the time, the moment that you're looking at it. It's always fixed. And here you can see what is the summation. Any question up to here? Okay, so now I want to solve an example to show you how you can solve for different parameters in your circuit. So this is an interesting example. Let me draw the circuit first, the information first. So what we have is a load that requires 480 kilowatt, and it has a power factor equal to 0.8 lag. And we also have a line that has an impedance of 0.005 plus J 0.025 ohm per phase. And what we know is that the RMS line voltage at load terminal is 600 volt. So whenever you have a three-phase circuit, what matters is drawing an appropriate and correct one-phase, single-phase diagram, which you're asked to do it here. So let's see what we have. I have a load that in each phase, it's I know that this load in each phase, it's consuming 480 kilowatt. Let me see if the power is per phase. Okay, So I know that this load is consuming 480 kilowatt. Because it's not saying that this is per phase, then it means that this 480 is the total power. So it's important to understand that what I have here is the total power. So if I want to draw a single phase diagram, I need to show the single phase power. So I need to divide it by 3 to show that this is a one phase power consumption. And then the power factor is going to be the same. The power factor is the difference between the angles, so it doesn't matter if I'm talking about 3-phase or 1-phase. It's always explaining 1-phase difference of the angle. So this is what I know about the load, and the power factor of this load is 0.8 lag. And let's call this terminal as AN terminal. Now, I do have a line, and the line has an impedance of 0.005 and J 0.25, not 2. So this is the impedance of the line. Now, what else I know? I know that the RMS line voltage at load terminal, let's find the load terminal. Load terminal is here, right? So I know that the line voltage here, the RMS of the line voltage, these two words are very important. So I have the line voltage and its RMS value. So RMS value is fine. I don't need to be concerned about it at this point. But remember that when you have RMS voltage, every single voltage and current you're calculating is going to be RMS value. So I don't need to do anything particularly at this point, but I have to remember that everything that I'm calculating in terms of current or voltage is also RMS. But the line part is an issue. So if I have the line voltage, who can tell me what I need to do here? What is the issue with the line, the voltage being line voltage? I have 600 here. Can you write it down here as 600? I want one student to figure out what is the issue. Can I write the 600 at the load terminal in my single phase diagram?
There should be a voltage drop from line, right?
So it says at load terminal because it's the terminal of the load, then it's here. I'm putting it here because of this explanation. If I wanted you to focus on this side, I would have said like the sending terminal of the line or the source terminal of the line. But here is the load terminal. So the location is correct. There is another issue here.
Do you have to convert it to phase voltage?
Exactly. So if I'm drawing the single phase diagram, every single voltage or current I'm plugging in should be phase value. So I cannot have a line voltage in my single phase diagram. And if I have a line voltage, in order to convert it into phase voltage, I need to do a division by radical 3. So this division by radical 3 is because I need to convert this into phase. Now I have a correct single phase diagram. Okay, so let's see what else we require to calculate for this problem. So here is asking for the magnitude of the line current. So I need to solve for the line current magnitude. Now, the interesting thing, there is a little bit of confusion here that you have to understand. There is two line definition. One line is referring to an element. So this element is the line, right? And another line means it's the opposite of phase. So we have the phase versus line. And that line means line to line voltage or line to line current, each line current. But this is line being the element. So you have to figure out which one it's referring to. Here it's the line in terms of the opposite of phase, because I already know where I'm supposed to look at for the voltage. It's the load terminal. But in this one, it's talking about the line current. And this line is basically referring to this line here. So this is the current it's asking for. So it's asking for the line current, and here line is the element or the cable that I have. So it's the cable current, which is going to be this current. So I need to calculate this current first. And in order to calculate the current of the line, so what I have to do, I know the power consumption. So I know the power, I know the voltage. So I'm going to plug them. Let's see what I have. I know the power factor, I know the power consumption, and I know the voltage. So this line, the line current, is the same current as the load current. So I'm going to focus on calculating the load current, and then I have, that's going to be the same as the line current. So I'm going to say that P for each phase is equal to the voltage of that phase multiplied by the current of that phase multiplied by the cosine of phi, right? So what I can do is I have the power here, and I do have the power factor, which is the cosine. I also have the phase voltage. So I can plug these three, and I can find the current of the load, which is the same as the current of the line here. So let me do the calculation, and then I have a question from this part. So hopefully you can answer my question. So P phi is equal to V in each phase multiplied by the current in each phase multiplied by the cosine of power factor. The power factor is 0.8. The power of one phase is 480 divided by 3. And the voltage is 600 divided by radical 3. So then I can solve for the current of each phase being 500. So if you plug all the number, it's going to be 557.3. Now, because it's asking for only the magnitude, this is the correct answer. But if it was asking for line current, there was nothing in terms of magnitude, this was not an acceptable answer. What is the reason? Why I cannot use this equation in order to solve for the line current? So what I'm trying to say is that this is correct if it's asking for the magnitude. But I have seen a lot of students saying that, okay, I found the current, even if it's just asking for the line current and not the magnitude of line current. So if I'm asking for the line current, then you have to give me the vector. I need to know what is the magnitude and what is the phase of the current. So you need to find both angle and the magnitude. But here it's asking only for the magnitude. So this particular equation is using the magnitude. These values that we are plugging here, they are magnitudes. So if you are looking for the magnitude, you can use this equation. That's a perfect equation to use. But if you are not looking for the magnitude, you're looking for the whole vector with the angle included, then you have to either find a way to attach the angle to this magnitude to make it a correct vector, or you have to use another equation. So let's assume that I just want to go with the same scenario, but I also want to figure out what is the angle. So if you are looking for the angle as well, then you have to focus on the power factor, because we know that the power factor is cosine of theta v minus theta I. So if I'm looking for this one, here is where I can find some information about it. So I know that the power factor is 0.8, and because the voltage doesn't have any angle, I can make this assumption that the angle of the voltage is equal to 0. So the angle being 0, this is 0. So I can say that cosine of theta I is equal to 0.8. So I can solve for the angle. The angle is going to be theta I would be 37 degrees. But because the load is a lag load, I need to add a negative here. So the angle is minus 37 with an angle minus 37 degrees. So using this equation, I can solve for theta I, but it doesn't really show me if it's positive or negative. But because I know that it's lag, so knowing the fact that the load is lag, I'm going to add this negative here. So if I'm asking for the line current, this is what you need to give me. You need to provide both the magnitude and the angle. The magnitude alone is not going to be sufficient. But here we are looking for the magnitude. So you're good if you have only the magnitude. Okay, the next part of this problem is, we actually solved this one. The next part is asking for the magnitude of line voltage at sending end of the line. So let me quickly draw the picture here. So here we have the line, here we have the load. We know the voltage here is 600 over radical 3 with an angle of 0. And this time, it's focusing on the voltage at sending end of the line. This is the line, and the sending end of the line is here. Here we are sending the power, and the load is receiving this power. So the sending end of the line is going to be here. What we are looking for is the voltage here, but we are looking for the line voltage. So first, I'm going to calculate the phase voltage at sending end of the line, and then I'm going to convert it into the line parameter. So in order to do that, I can say, I'm going to write it this way. So I'm going to write it in this form, that the voltage, if I call this as V, for example, VAN is equal to the voltage drop I have here, voltage drop across the line, plus the voltage drop across the load. The voltage drop across the load is known. It's simply 600 with an angle of 0 over radical 3. So this one is known. For the line, I have the impedance of the line, and I also know what is the current because I just calculated it in the previous step. So it's going to be VAN being equal to the line impedance, which is 0.005 plus J 0.025 multiplied by the current of line plus 600 over radical 3. The line current is equal to what we found in the previous slide. It's 557.3 with an angle of minus 37. So at this point, when you are plugging the current of the line, you're not supposed to just plug the magnitude. It should be the vector for the line, so line current. So if you just use the magnitude you found and forget about the angle, you're going to have a totally different answer. So be careful that when you are writing a KVL or KCL, any voltage or any current you're plugging in to your KVL and KCL, they're supposed to be vectors, including both magnitude and the angle. So you cannot just plug the magnitude. Remember, this is a very important comment, that KCL and KVL are not correct for magnitudes. So you cannot add the magnitude and say the magnitude of currents entering it should be equal to the magnitude of the currents that are leaving. If you include the angles in form of vectors, KVL and KCL will still be correct in our three-phase circuit or one-phase circuit. Anyway, so if we plug what we found for the current of the line here, then we can simply calculate VAN, which is going to be 357.51 with an angle of 1.57 degree. Now, this is the phase parameter. Whenever you have the single phase diagram, anything you calculate is going to be phase parameter. So now you need to convert it into line parameter. So if you need the line parameter of it, it's going to be VAB, for example. It's going to be radical 3 multiplied by 357.5 with an angle of 31.57. Now it's focusing on the magnitude, so the magnitude is going to be this portion. Any question here? Okay, so let's see what else we have here. The next part, it's asking for the power factor at the sending end of the line. So if we need the power factor at the sending end of the line, it means that you need to have the angle of the voltage here and the angle for the current here, and cosine of the voltage angle minus current angle will be the power factor. So power factor in a circuit is not going to be one single value. It depends on which element you're focusing on. If you're focusing on the load, then it's going to be the cosine of difference between the angles of the voltage and current of the load. If you're focusing on this terminal of your circuit, it's going to be the cosine of the difference between the angle of the voltage and current at this particular terminal of the circuit. So power factor is going to be different if you are focusing on the sending end of the line versus on the receiving end of the line, which we have the load at that side. So in order to solve that, what I need to know is the voltage for the angle of the voltage and the angle for the current. For the current, I have already calculated the angle. The angle was minus 37 degrees. So the current of this current is exactly the same as the current of the load. So I can use the same angle here. Now for the voltage, I calculated the voltage, but I didn't focus on, actually I have the angle here. So I calculated the voltage at this terminal. So I can use the angle that I have here. So it's 1.57. So I can just plug this 1.57, which is the angle for the voltage. I also calculated the angle for the current. So the cosine of this difference is going to be the power factor for me. So if I do the calculation, it's going to be 0.78. It's still lagging because all that I have in front of it is inductor. If you forget about it, you can also focus on the fact that the voltage is ahead of the current. The current is behind the voltage, so it's going to be a lagging scenario. Okay, so this is what I wanted to cover for today. Do you have any question on this example? Okay, so if you don't have any question, I'm gonna stop sharing here, and I will post the recorded video, and I will post the notes that I have here. I want you to study them, and in the next class, I'm gonna go through more example. Hopefully, we can have we can learn everything that we need in three-phase circuit. Thanks for attending the class, and I don't have anything else. Enjoy your day and use this time for practicing for your exam as well. Have a good one.